My name is Jose Nestor Pardurera. My master thesis was the design of a testing setup board for ADC PLL systems supervised by Professor Carlos Amori and Dr. Luca Bertolesi. Let me first describe the problem for testing mixed signal systems, systems that mainly included ADCs and PLLs. It was necessary to use many external sources, as we can see in this picture, because these components required many different voltage references and power supplies, which represented a problem for the measurements because the long cables connected to the system, so-called DUT, had a high inductance, and in turn they were very sensitive to environmental disturbances, which affected the test results. In addition, it was essential to include many low-noise voltage regulators together with trimmers in the system for accurately setting the voltages needed by the ADCs and PLLs, commonly between 0 and 3.3 volts, which was quite troublesome because the value of the trimmers had to be calibrated manually, so mechanically by the user, for carrying out different tests, which not only wasted time but also involved the human error in the test results. In addition, these regulators are trimmers occupied area in the PCB of the system, which increased the cost of manufacturing. By the way, the Arduino board shown in these pictures corresponded to the interface for programming the DUT. So as to cope with this issue, it was designed, implemented, and validated a board for testing mixed signal systems able to provide not only many high-resolution low-noise output voltages, but also the possibility to digitally tune them through an Arduino board or FPGA, as well as able to allow the user to turn them on or off, digitally read their voltage and current so as to check that the programmed values correspond to the actual ones, and program his own system, the DUT. The final product was the so-called Thesis board in this picture. Now let me describe the architecture of this board. The Thesis board can provide up to 12 high-resolution low-noise output voltages, so-called channels, each channel being able to provide a very stable voltage between 28 millivolts and 3.3 volts. With a high resolution of 2 millivolts and a low noise of 2 nanovolts per root of hertz, as well as a maximum output current of 1 amp. After estimating the PCB area needed to implement only one channel, it was noticed that it would occupy a lot of area in case of replicating it many times, so as to achieve a testing setup board with many voltage outputs. As a result, it was decided to split this board into 6 modules, so-called VREC modules, with 2 channels each and a motherboard, being the modules responsible for providing the high resolution low noise voltages, whereas the motherboard in charge of delivering these voltages from the modules to the user system, the DUT. In addition, the motherboard collects all the instructions sent from the PC through the Arduino board or FPGA to program not only the DUT but also the modules, to set the output voltage of their channels, to turn them on or off, and to measure their voltage and current. By the way, the modules were mounted vertically on the motherboard as shown in this picture, so as to reduce the size of the motherboard's PCB and in turn the overall size of the testing setup board. Now let me describe the modules. Each module comprises 2 channels of the testing setup board, as I mentioned before, and has as input an unregulated voltage of 5 volts plus or minus 5% provided by an external power supply. Furthermore, it includes an input low-pass filter used to considerably attenuate the noise coming from the external power supply, which consists of an LC filter with an RC damping network needed to decrease the gain at the filter's resonance frequency. Now let me describe the channels. Each channel, so-called proc LBR in this picture, consists of two LDOs LT045 in parallel, which are these two, and a digital port MAX 5496, which is this one, being the channel's input, the unregulated but filtered voltage of 5 volts plus or minus 5%, whereas the output, a very well regulated voltage between 28 millivolts and 3.3 volts, with a high resolution of 10 millivolts and a low noise of 2 nanovolts per square root of hertz, as I mentioned before. Now let me explain in detail the reason behind choosing this approach. Since one of the main features of the testing setup board was its low noise output voltages, it was decided to use linear voltage regulators, LDOs, instead of DC-DC converters, because the latter typically provide output voltages with ripple and switching noise, which are not suitable for noise-sensitive applications such as the ones involving ADCs and PLLs. The reference selected was the LT3045 from Analytic Devices because it was a high performance LDO with a low output noise of 2 nanovolts per square root of hertz, a high power supply rejection ratio around 100 dBs, and a maximum output current around 500 milliamps. In addition, because it not only offered the possibility to turn on or off the device, but also had a programmable current limit circuit which could be used to monitor the output current, its output current. Hence, for implementing each channel of the testing setup board, it was used two of these LDOs in parallel so as to achieve the maximum output current of 1 amp. Regarding the digital pot, since the sum of the current references of these LDOs together with the resistor connected at their set pin, so-called RZ, determine the output voltage of the channel, it was proposed to use a digital potentiometer as RZ such that the output could be adjusted from 0 to 3.3 volts with a resolution of 2 millivolts. The reference selected was the MAX 5496, which was a 3-wire SPI interface digital potentiometer that comprised a pair of 10-bit variable resistors, which were connected in series so as to achieve the output voltage range. By the way, these two resistors, so-called ballast resistors, were needed because in practice there was a mismatch between the parallel LDOs. I mean, they were not exactly the same, which would be reflected in a slight difference between their output voltages. Thus, these resistors were placed between the LDO's outputs and the load so as to adjust or compensate this difference. It was firstly tested and validated the modules individually, I mean not connected to the motherboard, since the main feature of these modules was the tunability of the output voltage of their channels. It was analyzed their static characteristic, I mean the input code versus output voltage transfer function. In addition, it was derived the resolution, the DNL and INL errors, so as to evaluate the performance of the modules. As a result, it was obtained that the transfer functions were quite similar to the ideal one, and the average resolution was approximately 1.93 millivolts, which represented the LSB and was quite near to the expected one, 2 millivolts. Moreover, the DNL was lower than 1 LSB, meaning monotonicity in the transfer function. However, the INL was higher than 1 LSB, meaning that the accuracy of the output voltage would be slightly affected by this nonlinearity. In addition, it was analyzed the transient characteristic of the outputs so as to compare it with the desired one. As a result, it was obtained that the real tendency was quite different from the desired one, although it reached the expected steady state, 3.3 volts in this case. This tendency was due to the fact that the two internal variable resistors of the digital pot cannot be programmed at the very same time, reason why the output reached first reached let's say an steady state, intermediate steady state, and then the final expected, the final or expected one, let's say. In fact, the interval between programming the first variable resistor and the second one, so-called t-proc, was about half second, which affected the settling time of the channel's output. Finally, it was tested and validated the modules together with the motherboard. I mean the overall system without the DUT. For doing so, it was analyzed the static characteristic of the channels, not only regarding the output voltage but also the output current. As a result, although all modules and in turn all channels were implemented with the very same components, it was obtained a variance between the transfer functions, which primarily might be due to the variance between the components. In conclusion, first of all, it was confirmed the operation of the approach to implement one channel of the Thesis board, two LT35 in parallel, and the digital port MAX 5496. In addition, the individual operation of the modules was the expected one. Moreover, it was demonstrated that the Thesis board uh, without duty operated as was intended. On the other hand, the variance between the components of each channel was the main factor to have a slight variance between the output voltages for the very same input code. Uh, Finally, the Thesis setup board was already used to test a mixed signal system, which was shown in one shown in slide 4, which corresponds to this very same picture, where the system is the so-called DUT here. This ends my master thesis presentation. Thank you for your attention.